In everyday environments, the dynamic range of scene brightness can vary greatly. As a result, to display augmented imagery on top of the high dynamic range physical world requires a high dynamic range display. We present an augmented reality optical see-through display with high dynamic range and scene-aware brightness adjustment of virtual objects. That brightness adjustment is applied spatially across the display using data measured from a horizontal array of 4 high-sensitivity light sensors. While our system targets use by a person, all results were captured by a camera located where the human user's eye would be located. In each example that follows, the camera has a locked shutter duration, gain, and frame rate. In most of the examples that follow, the augmented scene is a pair of spinning teapots located at fixed points on a large desk, located about 3 meters away from the user. The lighting model used to render the teapots is fixed and does not use any information from the light sensors. We first present a demo where the viewpoint is static and the system is configured to maximize the dynamic range to the full 16 bits without loss of detail. The brighter left teapot uses the upper 8 bits and the right dimmer teapot uses the lower 8 bits. This range exceeds that of the user camera, so we demonstrate the range by moving a neutral density filter in between the display and the camera. When the filter is present over the left teapot, note that both teapots are fully detailed. This filter cuts almost 98% or 34 dB of the light. We next present a pair of demos that use variable illumination and viewpoints, where the system is automatically adapting to the positional brightness of the scene. In the first of these demos, we move a pair of narrow beam flashlights of differing brightness around the otherwise dark physical scene. Note how each teapot brightens and darkens relative to the brightness and proximity to the spotlights. The brightnesses of the teapots also remains aligned to the teapots as the display rotates. In this demo, we present the same teapots but change the angle of a very bright desk lamp. Again, note the matched response of the teapots to the light. Last, to demonstrate the low latency properties of the system, we present another set of demos. Our system has about 124 microseconds of end-to-end latency on average. In this demo, we present the teapots with fixed brightness and move the display at different speeds. Compare how they seem attached to the desk with our latency compensation algorithm enabled, but slide across the desk with it disabled. The misalignment distance increases with the rotation speed.